Good morning to everyone. Yeah. So next one is cascade stays. You know about the cascade stays. So generally in the cascade, two transistors will participate. One is the common source, one is the common gate. Generally, the basic structure is like that. So what are the characteristics of the cascade stays? Cascade of the transistors will have more benefits. What is that? So increasing the voltage gain of the amplifiers and the output impedance of the current source courses. So while providing the shielding as well. So whenever we are providing the better shielding, then cascade stays will do the two things. One benefit is increasing the voltage gain, and also if there is a current source, then what happened? The output impedance of the current source is increases. These are the two things. The application of the cascade stays is high frequency amplifiers with relatively high input impedance. So for the purpose of to work at the high frequency, to amplify the high frequency signals, as well as what, to provide the higher input impedance. So that is the application of the cascade stays. So as I told you, a cascade of current source, common source stays and common gate stays. Okay, generally, so the basic structure we are saying like that. So common source and common gate, these two will be participate in the cascade stays. Okay, so what is the a cascade circuit offers high speed of so generally they are using the high frequency higher speed, provide the higher speed of application or higher speed of operation. Okay, so here in common source we have the common cascade stays. We have common source and common gate. The first is common source, then the next one is common gate. Okay, common source is for the higher input impedance, we are using for higher impedance, and common gate is used for the high speed. I hope you understand. So one is for the former is used for the more input impedance, and the latter one is used for the higher, I provide the higher speed. That is those are the features of the common cascade stays. Okay, cascade stays has two benefits. One is the voltage gain enhancement, one more is the output impedance of the current source enhancement. Application is one, so high frequency amplifiers. Okay, so to provide the higher frequency amplification, we can use this cascade stages. Moreover, to provide the higher input impedance. So generally in the cascade stays, so common source and common gate both will participate. So the first one is a common source, and later next one is the common gate. So common source is for the higher input impedance, and common gate is responsible for the high speed. That is the cascade stays characteristics and benefits. Okay, already we know. So just you can write like this: common source and common gate. These two will participate. This first stage is used for the first circuit or first device is used for the higher input impedance. This is for the high speed. That's it. Okay. So any doubt? Hello? Yeah.
No.
Yeah. So come to the point. High frequency model of a cascade stays. Okay. So differential pair with active load. Oh, sorry, this heading is not correct. Okay. So forget about this heading. Differential pair with active load. Just remember this circuit. This is the cascade stays. High frequency model of the cascade stays. This is the common source. This is the common gate. Yeah. So in this circuit, in this cascode stays. So node A is this. This is the node A. Okay, at the node A, CGS1, this is connected to the ground. See, this CGS1 gate to source of M1 is in between the node A and ground. Okay, and CGD1 is the CG1 gate to, this is the gate to drain is in between A and X, A and X nodes. Understand this one? At node A, okay, at node A, you have two capacitors. One is the gate to source one more is the gate to drain of M1. Okay, so gate to source capacitance of M1 is connected from A to ground, and so gate to drain of M1 is connected in between the A and X. Okay, so this is all about the node A. When it comes to the node X, this is the node X. At the node X, okay, so drain to body, this is the drain to body of M1, source to body of M2, and gate to source of yeah, this is, yeah, spelling mistake. This is gate to source of M2 are tied to the ground. Yeah, these are joined like this. This is one transistor. These are the two transistors. They are joined like this. And at node Y, this is the node Y. Drain to body. This is the drain to body of M2. And gate to drain. This is gate to drain of M2. And so CL. So maybe the load capacitor. They are connected to the ground. So now the Miller effect of. So here in this circuit, who will produce the Miller effect? So generally here, if you take this point, this will provide the mirror, because this CGD gate to drain of M1 is connected between the input node and this output node. So this is the Miller effect of CGD1 is determined by the gain from A to X. So what is the gain from between these two? From that you can find this Miller effect. Because if you want to apply Miller effect for this capacitor, then you will get one capacitor here and one capacitor here. This capacitance value is, you can say, CGD, okay, by 1 minus AV, and this is so CGD by 1 minus 1 by AV. This is the formulas. Okay. Now the Miller effect of CGD1 gate to drain of M1 is determined by the gain from A to, so X, A to X. The low frequency gain for low value of RD, okay, so is equal to, this is low frequency gain for the low value of this RD is equal to minus GM1 by GM2 plus GMB2. This is the low frequency gain. So because of RD. Okay. So these are the different components, different capacitors available in the cascode stage, which is at the high frequency for the high frequency analysis. Okay. And if M1 and M2 have roughly equal dimensions, if these two are identical transistors, means they have equal dimensions. So then gate to drain of M1 capacitance is multiplied by approximately 2 rather than the large voltage gain in a simple common source stage. So whenever if these two are equal, so in the dimension, then you can say this capacitance is multiplied by the 2, because of this is having one capacitor, this is having one capacitor, this is having one more capacitor. So that if both are equal in dimension, then you can say your CGD1 is multiplied by the 2. Okay. So next one is, so what is the, now from this circuit we need to calculate the poles. So what is the pole? So this is the pole frequency at node A. Pole frequency at node A. What is the formula? 1 by, so resistance into capacitance. This is the formula, 1 by RC. 1 by RC. So what is the R value here? R value is the source resistance RS at node I am talking. Okay, and find the equivalent capacitance at the node A. So the equivalent capacitance is CGS1 plus 1 plus GM1 by GM2 plus GMB into CGD1. This is the pole frequency at the node A. Okay, similarly pole frequency at the node X. So node X means this is, again find same formula 1 by RC. So that is equal to GM2 plus GMB by 2 CGD1, CDB1, CSB2 and GS2. Because what are the capacitances associated with this one? So with the X node, you have associated with 1, 2, 3 capacitors. So that 1, 2, 3, 4. 3 means here is one more thing is that these are the 2. 2, 3 and 4 capacitors are associated with the node X. So that you can write 4 capacitor values here. 2 CGD1 gate to drain 1 and drain to body 1 and source to body 2 and what is that one? Get to source of 2. And what is this R value? R value is nothing but 1 by, so that means here R value is 1 by, so GM2 plus GMB2. So that is the R value, this is 1 by. So that you will get the, so pole frequency at the node X is GM2 plus GMB2 by, so 2 times the CGD1 plus CDB1 plus CSB1 2 and CGS2. Yeah, I hope you understand. And this is the node A and this is node X. At node A, resistance is RS is associated with the node A and capacitance is CGS1 is directly available capacitor. One more capacitor is CGD1. This is the CGD1. One more capacitor. Okay, so whenever you are applying the Miller theorem for this fellow, then one capacitor will be come to this point, this side. That capacitor value is what? CGD1 is multiplied with 1 by, so gain 1 by 1 minus gain. Gain is what I told you. This is the gain. This is the gain. So that is, so 1 plus GM1 by GM1 plus GM2 plus GMB2. GMB2. This is okay. So that if you do the analysis, then GS1 plus the CGD1 is multiplied with GM1 by GM2 plus GMB2. This is a gain. Okay. So generally, whenever for a capacitor, if you apply the Miller theorem for this capacitor, Miller theorem, suppose C. So input capacity Ci is equal to C is multiplied with 1 plus A. This is the formula I told you. Miller multiplication of the capacitance. With that, so this is the Miller capacitor is multiplied with gain 1 plus, this is the gain A. So 1 plus A into what is that one? Capacitance is CGD1. Understand? Hello?
Yes, sir. Yes, sir.
Yes, sir.
So because the formula is Z by 1 minus A. This is the formula. Z means 1 by CGD1 by 1 minus A. A means what? This is. So like this. So if you take this, this is the Z formula. So inverse if you take, then Z means 1 by CS you will get. Then CS is equal to the total, the denominator will come. I hope you understand. That's why I'm telling you very casually. If you not understand, I will write it once again, no problem. Okay. What is the formula? Z1 is equal to Z by 1 minus or plus, you can say no problem, minus plus A. Here Z1 is equal to 1 by C1, you can write C1 is equal to 1 by C, Z means by 1 plus A. That is equal to 1 by C1 is equal to 1 by C into 1 plus A. What is the C1 value? What is C1 value? Hello? What is C1 value? Simply C is multiplied with 1 plus A. This is called the Miller multiplication of the capacitance. Input capacitor is always Miller multiplication of the capacitor. Okay. Hello.
Yes,
Yes,
sir.
sir. Yes, sir.
Yes, sir.
Yeah. So say with the same analysis, this is what 1 plus gain A. Of course, minus is there. For this minus is there. So minus minus becomes plus. And this is the capacitor CGD1. So I applied what is it, the Miller theorem for this capacitor. That's why I got, so input capacitance Ci is equal to this much. So now the frequency at A and frequency, pole frequency at A and pole frequency at X, we know. Now at Y, what is the pole frequency? Y is this node. Y is this node. So what are the capacitors associated with this one? So 1 and 2 capacitors. Okay, you can come down, and one more resistance is also directly available, Rd. Okay, so that 1 by Rd is multiplied with the 3 capacitors. One is the drain to body, one more is the load, one more is the gate to drain. So 3 poles, pole at A and pole at X and pole at Y. So we found it simply. So pole frequency formula is what? Pole frequency is equal to 1 by what is the frequency? Pole frequency formula 1 by RC. This is the formula. Okay, so you need to find how much resistance is associated with the respective node and what is the equivalent capacitance at that node. You need to find the 2 things. That's it enough. So wherever you want, apply the Miller theorem. Here I applied Miller theorem only at this point. Only applied for this capacitor only. Okay, don't forget. So don't apply here. And the gain of this transistor, the gain of this circuit is, this is, what is the AV? AV, small signal gain is equal to, or low frequency gain is equal to minus GM1 by and GM2 plus GMB2. Where it is required? It is required when you are going to find, when you are going to apply Miller theorem, then this gain is required. Okay. Yes. Miller effect is less significant in cascade amplifiers rather than in common source test. So the pole associated with the node A is, and the pole associated with the node X is, and at node Y is this much. Okay, all the poles. Okay, the relative magnitude of the 3 poles in a cascade circuit depends on the actual design parameters. Okay, so the pole frequency at X node, okay, is typically quite a lot higher than the other 2. This frequency is, that means this frequency is higher than these 2 frequencies. Yeah. So yeah, this is already about this capacitance. Roughly the capacitance is equal to, you can add all the capacitors here at X node. So what if RD is replaced by the current source? What if RD is replaced by the current source? So as to achieve higher DC gain. Suppose in place of RD, in the earlier circuit, if a current source is applied, what happened? Okay. In this circuit, in place of RD, if you use a current source, then what is this? Poles and zeros. That is my question. Yes. We know from chapter 3, that means chapter 3 is nothing but, what is the for chapter 3? Module 3 is nothing but small signal amplifiers. Okay, the impedance seen at node X reaches high value if the load impedance at the drain of M2 is large. What is impedance? Yeah, so for example, for CG common gate stage, input impedance Zi is approximately RD by GM plus GMB2 into R0 plus 1 by GM plus GMB. This is the common gate input impedance. So from this, you can predict that the pole at node X may be a lot higher, lower than. So this is, what is this one? GMB2 plus GM2 plus GMB2 by CX. This is including the body effect. If RD itself, it is an output impedance of the PMOS cascade current source. So interestingly, however, the overall transfer function is negligibly affected by this phenomena. This can be better seen by this example. Okay, I will see this example. Yeah, if you take this example, in this example, so consider the cascode stage. Yeah, this is the cascode stage amplifier, where the load resistance, see, here is what I told you earlier, here is a RD is there. In place of RD, I replaced a current source. RD is replaced with the current source, ideal current source, neglecting the capacitance associated with the M1. Okay, so in the M1 already, whatever the capacity earlier we have taken like this, so all are neglected. And now apply, what is that one? Norton theorem. Okay, for this, so input to V in M1, then you can get this one. You can get this one. Okay, so what is asking? So calculate the only transfer function is asking. So calculate the transfer function. We'll see how we can calculate, how best we can calculate the transfer function of this circuit. Remember, this is one cascade amplifier. Okay, so here is I think all the capacitors are neglected for the simplicity reason, simplification purpose. So, but major change is here is earlier RD is there. Now we have taken one ideal current source. Okay, so now neglecting the capacitance associated with the M1 and representing V in and M1, this one with a Norton equivalent circuit like this, and assume gamma. What is the gamma value? Is a body biasing. Okay, body effect value 0. Now compute the transfer function. Okay, in this circuit, in this cascade circuit, okay, in this cascade, the equivalent circuit is this one, because M2 is as it is, and current source is open, and M2 across R2, R02 is there, and CY is there. This is the output, and in the here this part, entire part is replaced with like this. This is the Norton equivalent circuit. Current source in parallel with a impedance is called the Norton equivalent circuit. Okay. So if V1, if Vn1, this is Vn1, much more negative than the, okay, leave it. Yeah. So now I'm doing some analysis here for the purpose of calculating the transfer function. So now current through Cx I want to find. How much current? Okay. So I can write the current through the Cx is the current flowing through the Cx is, I can write. What is the formula? I think this is the way, this is the V out. This is the voltage across this and this, because it's grounded. So these 2 points are joined. Then in this loop you have a, in this loop you have a, so V out, so that I can write to Cx is equal to, current to Cx is equal to minus V out, okay, by, I think Cy, by 1 by Cy, 1 by Cys, 1 by Cys, by 1 by Cys impedance. Okay, this is the current through this one, and one more current is I in. Okay, this current minus this current is this one, the current flowing this side, so that minus I in. So that is equal to, I can write minus V out, okay, into Cys minus I in. This is the current to the Cx. Okay, so once you know the current to the Cx, you can find the voltage. What is the node voltage at this point? Therefore, Vx, node voltage Vx is equal to, what is that one? Current is divided with the impedance. Current is divided, voltage is equal, sorry, current is multiplied with the impedance. Current is how much? Current to the Ix is, Cx is this much. So that this is the current V out Cys minus I in, this is the current. This is multiplied with the impedance. What is the impedance of this fellow? 1 by Cxs. 1 by Cxs. This is the voltage at node X. Okay. What is the small signal drain current of M2? What is the small current to the M2? Small signal. Small signal drain current of M2 I want. So I think you can write the small signal current to the M2 is equal to, whose trans conductance is how much? So GM2, of course, minus, is multiplied with, is Vx, is multiplied with Vx. Is called the, what is that one? Trans conductance is nothing but, GM is the trans conductance. Trans conductance is nothing but current by voltage. And this is the into voltage. Voltage will cancel and current will be remains. So that is equal to, so minus, so GM2. What is the Vx value? Vx value is, here is that. So minus V out into Cys minus I in by Cxs. Yeah, this is the small signal current to the M2. Now I want to find current to the R02. Yes. So therefore, current through R02 is equal to how much? So because some current is coming like this, some current is coming like this, and some is going this, and some is going this. So that you can write the current, whatever the current is there, this is the some current is going this side, you know this current, these two subtraction is this current. So this current and this current subtraction is this current, difference is this current, because three currents are coming. Yeah, you one is coming, and you can split like this, or it may be coming like this. You can add this is equal to this one, so that I can write the already you know the current to the Cx, current to the Cx. Okay, what is that Cx, current to the Cx, or current to the Cy? This one, current to the Cy is equal to, so minus V out into Cys. This is the current to the Cy minus, or sum of these two currents. So maybe coming like this and coming like this. The total is what a current to the R02. So that this is the other current. So minus GM2 into, so V out into Cys, so plus I in by Cxs. Yeah, this is. Therefore, V out, what is the V out? Total output voltage V out is equal to Vx plus VR02. Yeah, if you write the loop equation here, like this, then voltage across Cy is equal to voltage across R02 plus voltage across Cx. Voltage across Cx is nothing but Vx. So already you know the current to the R02, so that you can find the voltage across R02. So this is the current across R02 is multiplied with the R02. Okay, this current is multiplied with the R02 is nothing but, so voltage across R02 plus, and already you know the voltage across Cx is Vx. So Vx is there here, and you need to find R02, voltage across R02. So then, yeah, you can. I need one more. Have you note down this one? Hello?
Noted.
Students?
Yes, sir, noted.
If you complete it, I will erase this. Okay. Hello.
Noted.
Not just.
Okay. So what is that one? Total output voltage V out is equal to what? So V R naught 2 plus Vx. Vx. Yeah. This is the loop equation I wrote. So V R naught 2 is nothing but already you know the current to the R naught 2 is multiplied with what is that one? So that is equal to so minus R naught 2 into current to the R naught 2 is what? So V out into CYS plus V out. So into yeah, plus okay plus V out. This is okay. GM2 is there. Okay, GM2. Okay. So GM2 into V out 2 into CYS plus IN into GM2 by CXS. This is the current to the R02 is multiplied with the R02 is nothing but the VR02. And so Vx is minus V out CYS plus IN by CXS. This is. So therefore, I think in this equation, you have a V out equation. This is V out and IN is there. IN is the input, V out is the output. So that, so V out by IN is equal to, you got minus after rearranging the equation, GM2 R02 plus 1 by CXS is multiplied with 1 by 1 plus so GM2 into R02 okay is multiplied with CY by CX plus CY R02. Yes, this is the so V out by V in after rearranging the circuit. So suppose if GM2 generally it is correct. GM2 into is multiplied with the R0 is far greater than 1. And one more is GM2 into R02 into CY by CX is also far greater than 1. With these two approximations, I can write this approximate this circuit, this equation is, sorry, I can write this equation is approximately the above equation is. So in this place, minus GM2 into R02, yeah, plus, what is it? Yeah, this is multiplied like this. This is 1, you can use multiplication. Yes. Then you can write here this GM to R02 because 1 is negligible by CXS. And in the bracket term, what is saying? This 1 is negligible. Okay, because this is much more greater than 1. So that you can write in the denominator 1 by. Okay, so GM2 into R02 into CY by CX. Okay, plus CY into R02, yes, this is in the denominator. So now, further simplification, it can allow this R02 and this R02 get cancel each other. So that finally you have a, what is that one? That is equal to, so minus GM2 by CXS into 1 by What is that? So Cy by Cx into Gm2 plus Cys. Cys, that's it. This is the only the. So now this is the only V out by Vn, but we want V out by V out by Vn. Sorry, this is the V out by In, but I want V out by Vn. Therefore, V out, the ratio of output to the input voltage is equal to, so minus Gm1 into Gm2 by, so same thing. You can take the, what is that one? Yes, Cy take common in both cases, then Cy Cx, yes. So Gm2, this is Gm2 by Cx plus S. Yeah. So how did you get the V out by Vn? Simple. Already you know the, so V out by In. If you multiply this with the transconductance, Gm. What is the Gm? I by V. I by V. Okay, this I cancels, then V out by Vn is remains. Understand? Hello? అర్థమైందండి ఎలా వచ్చింది అది?
ట్రాన్స్ కండక్టెన్స్ తో మల్టిప్లై చేయాలి.
సో అందుకే Gm1 తో మల్టిప్లై చేశాను. Gm మొత్తం టోటల్ ఫంక్షన్ ని V out by V In ని Gm1 తో మల్టిప్లై చేస్తే నాకు ఇన్ టర్మ్స్ ఆఫ్ Vn వచ్చింది. ఎందుకంటే Gm వాల్యూ ఇస్ నథింగ్ బట్ కరెంట్ బై వోల్టేజ్ కదా. సో మీరు ఏ ఫైండ్ అవుట్ చేశారు మీరు? సో V out by V I ఫైండ్ అవుట్ చేశారు. సో దట్ ఈ I క్యాన్సిల్ అవుతే V out by Vn మిగిలింది. If it's okay, I will go to the next one.
Okay.
Okay. So now at last you can say about last transfer function. This is the final transfer function. This is actually required. So what is asking? He asked to find the transfer function. So I got the transfer function. Okay. So that is the, so Gm minus Gm1 into Gm2 by Cx into S into Gm2 by Cx plus S. Magnitude of pole at node X. What is the magnitude at the pole at X? Means this is. That means pole frequency. The X is equal to, so Gm2 by X. So magnitude at X, magnitude of the pole is equal to how much? So Gm2 by Cx. Because at high frequency, why I got this very simple pole is, at high frequency, this Cy becomes shunt to the output and dropping the gain of the circuit and suppressing the Miller effect of R02. So generally this is the R02 is presenting like this. So you need to apply for the R02 Miller theorem. But at high frequency, because of Cy is short circuit this one, so it neglect the application of the Miller effect to the R02. So it neglect the CD1. Suppose in this circuit, yeah, if you neglect the CGD1, sorry, gate to drain 1 of capacitance and Cy, if you neglect both Cy, then your output impedance is equal to 1 plus, this is the general formula, output impedance formula, Zx plus R02. This is the output impedance. How means? This is the impedance at the node is X. So Zx, you can write in Zx. Okay. And so this is the R02. You know the gain. This is plus R02. So that this Zx is multiplied with the 1 plus gain plus R02 is the total output impedance. Z out. Okay, so in this equation, here Zx is equal to what? Zx is nothing but R01 is parallel with capacity Cx, 1 by Cxs. Okay, so if you see the Z out, or substitute this Zx value here, then Z out is equal to 1 plus GM2 into R02 is multiplied with the Zx means R02 is parallel with R01 is parallel with 1 by Cx plus R0. Okay, so from this, so Z out has a pole. What is the pole? The term which is contained in the S. So the pole at Z out is equal to 1 by, see, if you take the parallel combination, then you will get the R01 into Cx. This is the pole frequency in the Z out trans function. Okay, understand this one?
Sir.
Hello?
Yes, sir.
This is the Z out formula. This is the standard formula which is already we completed in the cascade amplifiers. Okay. Here at this point or in this circuit, Zx means the impedance is here. What is impedance here? Here is the one transistor is there already. That is the what? M1 transistor. Across M1 there is a R01 is there. R01 and Cx both are parallel. If you substitute this Zx value here, then your Z out has a one pole, that is at 1 by R01 into Cx.
Yes, sir.
Hello?
Yes, sir.
Yeah, this is. So now come to the, so another one is differential pairs. Okay, differential pair. Yeah, differential pairs. So now the next job is find the transfer function or frequency response of the differential pair. So in this module, in the frequency response module, we computed the frequency response of common source. Okay. So next later, what is that one? Cascade. Next current sources, current mirror circuits. Now differential pair frequency response. What is the frequency response of the differential pair? Okay. So generally for differential pairs, okay, this is the differential pair circuit. We know this is the first A part is differential pair circuit, and this is the half circuit concept, and this is the equivalent circuit of the common mode inputs. Okay, so for differential signals, the response is identical to that of common source. Once again, remember, for differential signals, whenever V in 1 and V in 2 both are different, for this, the response is similar to the response of the common source CS stage amplifier. Okay, and exhibits the Miller multiplication of the capacitance of the CGD. So this is CGD. You can apply, what is that one? Miller theorem for this one. Then, so it will get the Miller multiplication of this capacitor, this side and this side. Okay. So whenever since your input is, that means your input is plus, since plus V in 2 by 2 and minus V in 2 by 2 are multiplied by the same transfer function. So are multiplied by the same function. The number of poles in V out by V in, number of poles. So for V out by V in is equal to, so this is the one input signal, this is one more input signal, plus or minus same or equal. Okay, at that time V out by V in is equal to, what happened? The number of poles in this transfer function, number of poles is equal to, so the poles in each path, the poles in each path. So in this path and in this path. Okay. See one more thing. So for the different signals, the response is entered into the CS amplifier, and the Miller multiplication is applied to the gate to drain capacitance. And since that means both the signals are okay in common mode, both are half of the inputs with different polarities, so are multiplied by the same transfer function. The number of poles in the transfer function is equal to the each path. Each path means one left hand side, one more is right hand side. For common mode signals, the common mode signals, the total capacitance at node P is here. This is the node P. What is that one? The total capacitance of the node P. You can compute. So from the high frequency gain. Okay. So and the capacitances gate to drain 3. This is third, this is the gate to drain 3. This is the gate and drain 3. And drain to body 3. So drain to body 3 means you can draw like this here. So C drain to body 3 plus source to body 3 GSB 1 and source to body 2. Source to body 2. So this is the, what is that one? Yeah, C C GD3 C DB3 C SB1 and CSB2. So source to body of these two transistors, and gate to drain and drain to body of this transistor. So two capacitors for, because of this third transistor, and so these are the because of each transistor. Okay, so this capacitance can be quite substantial if M1 and M3 are wide transistors. M1 and M3 are, these are wider than this one, M2. Then this capacitance can be small thing. Okay, so this circuit, generally differential pair circuit, what will do? So circuit will convert the input common mode variations to a differential error by a factor which is equal to. So this is the I'm writing this formula from the previous module, differential amplifiers. Then this is the gain that is Cm minus Dm is equal to, we have found there, delta Gm into Rd by, so Gm1 plus Gm2 into RSS plus 1. This is the formula we calculate in the differential amplifiers. Here, what is the delta Gm? Where delta Gm is equal to Gm1 minus Gm2. Okay, so here replace R03. Okay, R03 is equal to, so R03, wherever R03 is there, means R03 means this transistor resistance R0 is replaced with R03 is parallel with capacitor, this one by CPS, because these two are parallel, and RD is RD, this RD value, or this RD value, or this RD value can be replaced with RD is parallel with, it is a load capacity in each branch, so that 1 by CLS. So what is the CL? So total capacity seen at the each output node. Now if you substitute these values, this and this values in this equation, then so AV voltage gain of CM is equal to, so minus GM delta GM, sorry, minus delta GM. In place of RD, what is that? This is, you can write RD is parallel with 1 by CLS by, so GM1 plus GM2, GM1 plus GM2 is multiplied with, this is the RSS, means this R03. So R03 is parallel with 1 by CPS plus 1. This is, understand? Hello?
Yes, sir.
Yes. So now, how much time is there? Yeah. So couple of minutes, I will complete this one. So after this, I will erase this one. If you want, you can take the snapshot. Yeah. So now, whatever the equation we got, that is the, I am writing once again here, minus, so AVCM is equal to minus delta GM is multiplied with RD is parallel with 1 by CPS by GM1 plus GM2 is multiplied with R03 is parallel with 1 by CLS plus 1. This is the final equation. So from this CMRR value, the CMRR common mode rejection ratio, CMRR is approximately equal to, generally it is understand that the CMRR of circuit degrades at high frequency. So that is equal to, so GM by delta GM into 1 plus 2 GM into R03 is parallel with 1 by CPS. Okay, this is actually the CMRR formula. This formula is from the previous module, that is the different amplifier module. So now I can write in place of this, I can apply GM by delta GM. So in place of this, what is there? We have, so what is that one, parallel combination of these two is nothing but what we'll get. So R03 CPS plus 2 GM into R03 by R03 into CPS plus 1. This is, So already you know the GM value, GM1 plus GM2. GM is equal to here, GM1 plus GM2 by 2, sorry, half GM value. Okay, now, so in this transfer function, numerator, if you see the numerator, is the numerator having 1 0, 1 root. Okay, what is that 0? The 0 is that, see, this is the S term, this is, so that make it as coefficient is 1. Then this by this will come. So that 0 is at 2GM, 2GM R03 by R03 plus, sorry, R03 CP. Yeah, CP. R03 CP. This is 1 plus, of course. This is at the, this is the 0 frequency. And see the denominator, this is the denominator. Again, 1 root is there. That is called the pole. The pole is at 1 by R03 into CP. So if you take these two, this is the 0, this is the pole. So because of in the numerator, there is a GM term is there. This is higher than this fellow. The magnitude of 0 is more than the pole. Okay, how much? So if you take, if you draw the circuit, if you draw the frequency response plot, so I'm clearing this screen so that if you want, you can take the snapshot. So then, yes. Yeah, see, this is, yeah, this picture. So this is the pole. No, sorry, this is 0, and this is the pole. Since this value is, neglect this one, this value is much more than this value. I think 0 frequency is more than the pole frequency. Where is the pole? Pole is at 1 by R03 CP. This is the pole. Where is the 0? 0 is at 2GM3 by 2GM3 is multiplied with the R03 by R03 into CP. R03 cancel. 2GM3 by CP is there. This is. So, for example, this 0 dB gain, because pole is present first, it becomes minus 20 dB slope. Then, because 0 is existing here, again the minus 20 dB plus 20 dB, then it becomes 0 dB. This is the CMRR of differential pair versus frequency. This is the CMRR value, how it is changing with respect to the frequency. So here is 0 dB, minus 20 dB, again 0 dB we get. So this transformation, CMRR transformation has 1 pole and 1 0. The 0 magnitude is much more greater than the pole magnitude. That's why pole will come first, then 0 will come later. Understand? Hello?
Yes, sir.
So then I will stop here. In the next class, I will start a new topic. So that means module 5 or module 5 first I will start. Okay.